And those who look at the printed program see Raviv's name here. He was supposed to be here. Unfortunately, he couldn't come, so I'm doing the speaking. This is a work that we both are involved in. So I'm going to talk about, again, using data analytics for hardware verification process. So I'm talking about verification of the hardware, meaning the process that we are doing to ensure that what we designed actually matches what we plan to design, what the specification says. And in many cases, this is a very big and complex process. So, for example, if we build a new processor like a new ARM-A architecture core or something like that, this is something that can take many, many months, use tens or even hundreds of people, and use also hundreds of machines. And of course, in this kind of process, we need means to understand, control, and see what's going on in this process. And what we are going to talk about is how we use analytics to do that kind of work. So before we go and talk about verification in the information edge, let's start at the very beginning when hardware design were simple, just few logical gates connected and doing some very simple function, and then verifying it, making sure that it worked correctly, was the designer writing some kind of vectors, running them through the designs, and getting into the output, see that it's behaved correctly, and everybody was happy. But then things got more complicated, and we need to invest more effort. So we started to add some automatic checking mechanisms, so something that can tell me, by a machine can tell if the behavior is correct or not. And if I have something that can automatically check, then I can put some more randomness in the input that I'm getting. I don't need to write my specific vectors that are not what they are going to be. And from that, we evolved into a process that nowadays is highly automated process, meaning that we have, again, as I said, hundreds, maybe thousands of machines that running verification jobs that basically create tests, run them through simulation on the design, check the results, collect coverage data to make sure that I'm checking everything, and repeating this process over and over again for the period of the project. And in that kind of project now, we try to see that we have a lot of information, and we get to the information edge. That's where we are now. So the verification process, as I said, becoming increasingly interconnected. We have a lot of different processes, sub-processes of jobs that running, that are doing smart things and are generating data. And while this data is available, nowadays it's not being used very much because, again, we have a lot of it. So experts have their own ways to say, looking, for example, at the curve of bugs that I'm finding and says, oh, I'm in good situation, I'm going to be able to flat out find all the bugs before I schedule to tape out, send the process to silicon, or I'm finding too many bugs, I need more resources here or there. But this is the level of things that's being done. So looking at it in a slightly different way, as I said, we started the process, so when we did things very simply, but also we have very little information to look at and understand what we are doing. And this is actually continued even through time when we start to use a lot of automation. But then we discovered that we have a lot of information in our arsenal that we can use. So for example, we have coverage. We have some monitors in our designs, in our environment that tells us what we are checking, what we are exercising, what we are checking and what not, and we can tell how good we are. So this is one source of light that tells us what's going on. We have, of course, information about failures, where they are found, how they are found, where the bug was located, and so on. This is another source of information that we can use. We can also, each job that we're running, each simulation, each test case, actually produce some kind of a log saying what happened. We can use this kind of information. So we move from that kind of state where we were blind to a state that we are actually now have maybe too much information and we are drowning in this information. We don't know what to do with all this information. We don't know how to use it efficiently. And again, this is what I'm going to talk about and see how we can do that. So data analytics is the things that we're going to do. And the definition coming from Wikipedia is a process of inspecting, cleaning, transforming, and modeling data with the goal of highlighting useful information, suggesting conclusions, and supporting decision-making. Data analytics has multiple facets and approaches, encompassing diverse techniques under a variety of names in different businesses, science, and social science domains. So what does it mean to apply analytics techniques? So we're going to use things like, first of all, visualization. Just showing the data in the right way can help a lot understanding what's going on and extract meaningful information. We can use more heavy tools like machine learning, data mining, and all kind of other data analytics approach. And from that, we can actually get 3 levels of benefits. First of all, we can look at the data and provide deeper, better understanding of the data that we have, and from that, of the underlying world that it represented. So if we see data about failures, we can say, okay, that means that the design is healthy or not, and so on. But we can better do is by looking at the data and what's going on right now, we can say, predict what the future will be. So the example I gave to begin with, we look at the curve of the bugs that we are finding in our design, and we says, okay, in the next months, I'm going to find 50 more bugs in my design, and then the curve is going to slow down. So probably in 2 months, I'll be in a position where I'll be ready to send my design to manufacturing so I can start testing the real silicon. But if I can predict the design and I understand what action that I'm doing affect the behavior, then these tools can also provide the aids to make decision on how to improve my state. So if I'm saying that I'm going to find 50 more bugs in the next months and then things will be okay, but I need to tape out in 1 month. And then I said, okay, maybe I need more resources, maybe I need to change the way I'm doing things in order to be able to find the 50 bugs in 2 weeks, not in 1 month, to be able to meet my deadline. So these are the type of analytics that we are going to do. And again, what I'm describing here is how we are going to use data analytics as the backbone of a verification process. So the main objective is to use all this kind of data that I said that we are collecting during the verification process, and the connectivity between various data sources that we have, like the job scheduler that schedule verification jobs, the coverage collection, the failure data, the test plan, and so on, to improve the quality, the efficiency of the verification process. And the key ingredient to doing that are 3, basically. First of all, we need to instrument the data sources. So we need to make sure that, first of all, the existing data that we are aware of are inspected, the data is collected, we maintain history wherever we need it. We also need to find maybe new data sources that we haven't thought about and collect them to the system. The second thing is connecting all those data sources that I say can come from various different places and bring them into a central point. Again, in the work that we are currently doing, this is a real central point, a data warehouse that collects all the data, but there are other approaches that knows how to handle this data in a more distributed way. This is just a methodology of operation. I don't have anything to say that makes this one or this one much better than the other. And finally, once we have all the data in one place, we can start on using the intelligence and do all the analytics techniques that I talked about to do data analysis and provide us all the information, prediction, and so on about the process. So the vision is fairly simple. We have this functional verification process that is running. And as I said, this process has a lot of data and a lot of data that belong to a lot of sources. And what we want to do is take all these sources, extract the information out of the data, apply some decision support mechanisms, again, starting from simple visualization to deep learning and such, and provide ways that will allow us to optimize the process, change the way that we direct this process, and so on. And doing that with the three types of analytics that I mentioned, descriptive tells what we are, predictive tells what's going to be, and prospective that tells us how we're going to change or what to do in order to change the situation. And what we want to have is a consolidated platform for planning, analyzing, and optimizing the large-scale verification process. And again, I'll say it again, we are talking about very large processes that handling very large data. So this is a nice, simple picture that I draw, but there are many challenges that we need to handle. First of all, we have many sources that are independent, and even again, I'm coming from IBM. IBM relies a lot of its own tools, and therefore, you would expect that our tools would talk in the same language. They are definitely not. And if you are some other hardware design house that using the tool for the test plan from one vendor and the tool for scheduling job for another vendor and the one that collect coverage for a third vendor, you need to make sure that first of all you get all the data out of them, bring them to the data repository, and then connect them in such a way that they will be able to understand each other. So they'll talk in the same language. And the way to do that is basically to create some layer of translation that takes the data in one language and translate it into the common vocabulary that you manage your central data server. The second problem is that most of those tools that I mentioned actually having their own database. But these databases are what we call the operational database. These are databases that are optimized for handling transaction, mainly insertion, but also some level of manipulation, deletion, and so on. They are less efficient in operating on large sets, handling queries that looks at all the records and finds certain records of a different type or find some kind of a trend in the records and so on. So we need a different kind of database system to store the data that will allow us to manipulate it, get it out for the analysis that we want to do. And finally, we are talking about huge amount of data. So we are running millions of tests per day. We have hundreds of thousands of coverage events that we want to track. Simulation takes billions of cycles per day. We have a lot of data that is structured, so whether a test case covered event A, B, or C, this is a very simple structured database that fits nicely into relational database. But if we want to look at log data, this is unstructured, so we need to be able to handle this kind of structure. And for that, we need to decide what is the trade-off between the data that we store. We cannot store everything, so we need to decide on what granularity do we store. The coarser the granularity is going to be, we're going to lose some accuracy, we're going to lose some information, but we're going to have smaller data, and therefore it's going to be easier to analyze and probably be able to provide faster results. And finally, we need to know what to analyze and how to do that. And this is the rest of the talk. So there are many questions that we want to, or we can answer with the analysis. I'm going to focus, if I have time, on 3 of them, if not as much time as I have. So first of all, as a designer or verification lead, I would like to know which areas or which function or which source file in my unit are at risk. And by at risk, I mean I will find a bug in them in the next week or in the next few days. A second question is, as a verification engineer, I would like to know which test should I use in my nightly regression to maximize the efficiency. And the third question is, as a verification lead, I would like to see a quick and concise informative view of the status of my unit. So let's start with the regression test quality. The goal here is to rank the regression tests that I have according to their ability to fulfill the goal that I have, and goals can be, we can have many different goals, like finding bugs or targeting areas that I recently changed, or improve the coverage, or any other goal. And what we are going to do actually here is a very simple statistical analysis. So sum some numbers, divide by other numbers. So a test is effective, test A is more effective than test B if for 100 runs of test A, I find 1 bug, and for test B, I need 200 runs to find 1 bug. So in terms of finding bug, A is more effective than B, and this is very simple statistics that I can run. And then the problem is that, again, I have the data coming from many resources, like job submission tell me how many runs of test A, test B, and so on I had, from defect tracking, how many bugs I found and which test find them, from coverage, and so on. And so what I'm going to do is actually maintain sort of a probabilistic matrix that tells us what is the probability of hitting rare events, how many effects I'm finding. And this is what I'm going to display, and this is how such a report looks like. And by the way, these are all screenshots of real reports coming from the tool that we are using, which is Cognus. But again, this is not necessarily the tools that you need to use. But what's nice about it, that once we have this data, actually all we need to do is feed the policy that we want, how we want to split between, for example, these 2 goals that I have. And then we can take the top, run the report, take the top lines there and feed them back to the job submission and get the results that we want. Second thing that we do is say identified problematic files. As I said, files in which I'm going to find bugs in the next few days. And this is a classical machine learning regression, or actually classification problem. We have many features, like how many commits we did, how big are the commits, how complex is the file, which files are committed with it, and so on. We apply, we give some estimate of risk to the file, And we also determine the threshold that above which we said, yes, you're going to find a bug, no, you're not going to find. And we do that to get that kind of report. And here, unfortunately, I have to mask the name of the files because they may reveal some secrets that I don't know. But we see that we have 3 files that we consider are in risk, and the rest of the file in the unit, and there are actually much more than 10, are not at risk. Finally, we have a more complex things. We want to see what is the current status of the unit or the verification process. And this is something that we want to look every morning when we come back, or we want to focus on a status meeting. We want to drill down. If we look at every morning, we want to drill down to get details if we see problematic areas. And the method is we basically we have a large set of measures. They are fairly simple measures, like how many jobs I ran the last day, how many of them fails, how is my coverage improving, and so on. For each of them, we give them a grade based on a predefined model that determine how they're supposed to behave, a fitting of what we see to the model, and then how much we diverge, or we currently diverge from the model with the parameters. And again, this is how the report looks like. So we see the data over time, but what's more important, we see some gouge that says most of them are actually in normal position, some of them in a little better than normal, some of them are worse. So, and then what I can do, go to the one that I think in a bad position. These are, in this case, jobs that failed before they started simulation, go and investigate why this is happening, and so on. So to conclude, we have a process that produces tons of data with many tools that tweak in many languages and produce a lot of data. We want to extract useful information out of it, provide deep understanding, again, predict the future and help us improve the future. And we are doing this using all sorts of data analytics techniques that we apply. And to build such system, we need, first of all, as I said, well, we are using central hub. It can also be a distributed hub to connect the data sources, verification tools that are open and allow us to connect to this hub, and the IDs method for extracting information and analyzing it. And of course, for this, we need collaboration between users, vendors that provide the tools, and data analytics experts that can help us do the analytics. So thank you very much.